math problem, at least as far as the math in this course goes. It would specifically look like that right there. So that's actually the formula in the problem right there. And that would give you 0.67, which would be 67% if you need a percentage. Okay. Does anybody have any questions? Okay, fantastic. Then, does anybody have any questions about Chapter 13? Or would you want me to go on to Chapter 14? Okay. No questions, Chapter 13? No. Okay. Okay, right on. Then Chapter 14. All right. So don't forget, I'll be gone on Wednesday, and that's kind of the last lecture. There'll be a video lecture. I've already posted that. That video lecture is for the entire of Chapter 14, which you won't need the entire thing, so you can just skip forward in it. It is essentially the same material. I don't think I've changed the slideshow much since the last time I did that. You'll notice if you look back through my notes, like Chapter 13 got changed a lot. Okay? But that slideshow hasn't changed much. The intro to electrochemistry hasn't really changed much in like 100 years. So it's like, this is the basis of things like batteries, right? This is the basis of things like electronic detectors. So pretty well understood concepts. Okay. Now, interestingly enough, this is kind of a funny example of how things have changed over time, is that you can actually distinguish new from used alkaline batteries by comparing bounce height. So if you literally just bounce them and see how high they go, let's do it again. You can actually tell if it's a new or an old battery. You can use this yourselves, by the way. You just take a battery you know is used and a battery you're not sure about and bounce them. Well, that's going to depend on the bounce height, right? Okay. So this is actually the chemistry that's happening inside of a battery. And you can see that we have a combined overall reaction like this right here. Whenever you're looking at reactions, what do you have? You have a reduction and an oxidation side, right? So remember that you're always going to be comparing redox reactions, reduction, and oxidation. All right, so electrochemistry. This is going to be a branch of chemistry, really, but also analytical chemistry that uses electrical measurements of chemical systems for analytical purposes. So this would be the analytical portion of electrochemistry. Now, you can actually do things like, you may have noticed that the neurotransmitter measurements we did in Chapter 1 that we talked about a little bit, these were actually in electrochemistry setup. This can also refer to using electricity to drive chemical reactions towards produce, or you can use chemical reactions to produce electricity. Notice that this is what happens in your chargeable batteries for like a lithium battery, right? But also a metal hydride battery. Okay. Do you guys know what a metal hydride battery is? No? Oh, okay. So they're a type of rechargeable battery that's less energy dense and has a much larger number of cycles it can go through, like thousands of cycles. Okay. So they're the type of battery, if you want like batteries for your remote, that's the type of battery you'd want that you can recharge and reuse for decades. Okay. You don't want lithium ones because over time they'll degrade much faster, and when they degrade, they light on fire. So they're a much worse use for rechargeable batteries around the house. For your like powering your car, sure, they're great. Or powering the house for that matter, also great. Now, some of the desirable attributes of electrochemistry for analytical purposes is going to be it's a very relatively inexpensive equipment. In fact, you can oftentimes find these if they're really, really cheaply done in like a factory en masse. You can find these done for like 25 cents a test sort of stuff. Okay. And so of the methodologies I've talked about with you, these are the cheapest produced singular tests for. Okay. Now, instrumental, which we'll cover next semester, and is going to be differentiated a little bit from electrochemistry because it's things like using light spectrometers, photospectrometry. Those are very, very expensive in the upfront cost. Okay, you have to buy the instrument, which can be very expensive. Even visible light instruments typically range in the like $500 plus range. And so you can buy an electrochemistry probe for like 25 cents. They sell them in Africa for 25 cents that can detect various different diseases, in fact. Okay. You can potentially miniaturize these. Again, you all know that the probes and how small the electrical probes can get are just incredibly small now, right? That literally a grain of rice is bigger than some probes. Okay. The ability to measure some complex samples with little sample preparation. This one's a little bit, it is possible to measure some very, very complex samples very specifically with these probes, okay? If you design it correctly. But the designing it part can be incredibly complex to do that, okay? Though in some cases, it is really, really easy if you happen to have a voltage difference that's very large. Okay, so there are a few cases where this is actually incredibly easy, but for the most part, that complexity has been moved to designing for a lot of these things. Okay, not that it disappeared. So let's talk about some base reactions that we have to deal with. We have the redox reaction, of course. Redox being reduction, oxidation, right? And so you're going to have an oxidation and a reduction. When you're looking at a redox reaction, there's always going to be that set. Okay. And so this right here is going to be our oxidizing agent. What do you notice about this iron here? What's happening to it? Gains an electron, right? So oxidizing agents are going to gain electrons. Reducing agents are going to be what gives the electrons. Okay. Remember that when we're talking about these, the agent is the one that does that thing. Okay. And so the redox reactions, these are always going to involve the transfer of electrons from one species to another species. Now, you may know from like another course, like a biology course or organic course, or maybe biochemistry, that these redox reactions are oftentimes kept track of by keeping track of the hydrogens and the oxygens, right? So if you gain hydrogens, typically that's considered a reduction. If you gain oxygens, that's typically considered an oxidation in those fields, okay? But it is the exact same reaction. It is a electron transfers happening. The hydrogens and oxygens are just very convenient ways of keeping track of those whenever we're talking about like a biological condition. So oxidation, this is going to be, again, your loss of electrons. Reduction is going to be your gain of electrons. Again, the oxidizing agent can be called the oxidant, is going to take electrons from another substance and is going to itself become reduced because it gains an electron. Electrons are negative. That's going to be a reduction of it. Okay? So remember that the thing that's reduced is the oxidizing agent. It oxidizes something else. Okay? Now, oxygen is a very good oxidizing agent. Okay? It oftentimes is the oxidizing agent in most of these reactions on the planet. Okay? Now, reducing agents, this can be called a reductant as a reducing agent. So it's going to give electrons to another substance. It will itself be oxidized in the process because it will lose an electron. Okay. All right. So if we look at this again, Iron 3 plus right here, right? It is the oxidizing agent. So what is happening to that iron 3 plus? Is it being oxidized or is it being reduced? So it gained a negative charge, didn't it? Yeah, it's reduced. Went from a more positive thing to a less positive thing. That's reduction. Okay? So that was reduced. This right here is the reducing agent. So what happened to the V2 plus right there? It has to have been oxidized. Exactly. Okay? Very good. If one thing loses an electron, what has to happen to the other thing? Gain an electron. Okay? And you can pretty easily just go through and remember that thing that got the electron, reduced, right? Thing that lost electron, oxidized. Okay? Note there can be other species in here that don't really take part in the reaction. Okay? We have written a reaction where we have only the reacting species. We have gotten rid of all of the spectator ions. Okay, so Michael Faraday, 1791 to 1867, discovered the extent of electrochemical reaction is proportional to the electrical charge passing through a cell. Faraday discovered many of the fundamental laws of electromagnetism, gave us things like the electric motor, electric generator, electric transformer, terms like ion, cation, anion, electrode, cathode, anode, electrolyte. Those were all Faraday. Okay? So in case you've wondered where that name comes from, that's Faraday. The electrical charge, this is going to be designated capital Q for the symbol. So electric charge, this is the quantity of the electricity. So electric charge is going to be measured in coulombs, and that's typically designated capital C. So a single electron or proton is going to have a charge of 1.602 times 10 to the negative 19 coulombs. The Faraday constant, which is designated F, gives the magnitude of the charge on a mole of electrons. So if you were to take this number here, multiply it by a mole, 6.022 times 10 to the 23rd, that's going to give you a Faraday's constant. And again, that's going to be coulombs per mole. So this right here is actually the relationship between the charge and moles. So you have Q equals the number of moles times Faraday's constant. Okay. Notice right here we have an N here. See that? Okay. This is the last thing that's in there. And so this right here is the charge per molecule, because not every ion is a +1 or -1, right? And so this, for example, would have an N of what? 3, right? We'd have a +3 charge for each of the irons. Okay. And that's that formula applied for the iron that we just were talking about. And it gives this for the charge of that 1 mole of iron. Okay, so if 5.585 grams of iron 3 plus were reduced in that reaction we just talked about, what charge in coulombs must be transferred from the V2 plus to the Fe3 plus? Okay, I'm going to give you about a minute. Start working and try this out. By the way, keep in mind over the break that you do get points for doing late homework. So if you have homework that you have not done, you want to catch up, it's -1% off per day, right? Okay. And so doing the stuff that is less late will probably behoove you more overall. Okay. If you guys wanted to do a super duper study group on Monday and Tuesday, I guess you could. All right, let's go ahead and get going. Okay, so we're just going to use that formula that we just talked about. charge equals N times moles times Faraday's constant. Remember, again, this is a constant. This is what that F that kept being given to you on that table that you've been seeing all semester on all the exams. That was that F. So we have, in this case, we have one electron being transferred, don't we? And so our N, the charge, is 1. We then have 5.585 grams. This is going to be divided by the molar mass, or atomic mass in this case, and that is 0.10000. You may have wondered, why is this such a weird number? So that this number could be easily calculated. Okay. Now, that's the number of moles of the Fe3+. Each of those Fe3+ is going to take one electron, and so we'll have the same number of moles of electrons being transferred. This then is going to be multiplied by Faraday's constant, and is going to give us our charge, which is in coulombs here. Everybody good with that? Anybody have any questions? All right, so electric current. This is the quantity of the charge flowing each second through a circuit. And so this is going to be the unit ampere, abbreviated A, but oftentimes abbreviated AMP, capital A, lowercase mp. Okay. 1 ampere is going to represent the flow of 1 coulomb of charge per second past a point in the circuit. Notice that this can actually cause some kind of weird divergences in DC versus AC. Do you guys know anything about DC versus AC? No? Yeah? Okay. So electricity, when it's being used, there's 2 forms of electricity. There's DC and AC. DC, direct current, AC, alternate current. Okay? And so direct current electricity actually looks like this. If you were just to use like a power generator, you would get something that looks like this. Okay? And so, and this would be your maximum. Let's call that 120 volts. This would be negative 120 volts. Okay? All right, so typically what you would do on a normal circuit is you would touch this with your wire, and then you'd come over and you'd ground that in the ground, and that would give you 120 volts going back and forth. Like that. Okay? Along your wire. Back and forth across it. Most things, doesn't matter. Okay? Running a fan, doesn't matter. The fan's motor has to alternate anyways. No big deal. Light bulb, you don't really care if the light bulb is going to have electricity move this way or this way. It still lights. So it doesn't matter. Okay? Most things just doesn't matter. Analog, very easy. Your computer, it matters. Okay? Anything that builds up electricity very much matters. Okay? And so this is DC, and what they do is they just chop off everything on one side. And so what you then get is a collection of waves that come along in one direction. Okay? There's actually more complicated ways to do it, but that's the majority of ways that they do it. Okay? Now, do you guys know what a live 1, live 2 is? Okay. You ever heard of split phase? No? Yeah. Okay. You are aware that there are 240 volt sockets in the United States of America? Okay. So a normal socket is what's called nominal 120 volts. And that means that the electricity ranges somewhere around 120 volts. And so what actually happens is you get maybe 130 one time, you get 120, you get 125 maybe here, and it bounces around a bit, okay? Now, what you do here is you have another phase that's like this, okay? It's running through another wire. So this is L1, this would be L2. Live 1, live 2. This other phase would be the negative 120. So what's the difference between 120 and negative 120? 240. That's the difference, right? Okay. And so that gives you 240 volts, right? That's actually how you get 240 volts. Essentially what you're doing is you're pushing both ways against the central object in terms of potential. Okay. Okay. So those right there were potentials. All right. And they're having a potential that goes back and forth. Right now, you have a potential of being up here on the third floor in this case. Excuse me. And, you don't necessarily have to jump off, right? We're not currently jumping off. That's a good thing. Okay. So amps is going to be the amount of that current that moves. Okay. So that's going to be the amount of the charge that flows through each second through a circuit. And keep in mind that this is going to be directly related then to the number of electrons that flows through that circuit. Is that making sense so far? Okay. Okay. So 1 ampere is going to represent your flow of a coulomb of charge per second past some point in the circuit. Typically, it's going to be a point that's like on a meter, or it's going to be a point that you can measure in some way. Okay. Now, suppose the electrons are forced into a platinum wire immersed in solution containing SN4+, which is then reduced to SN2+ at a constant rate of 4.24 millimoles per hour. How much of that current passed through the solution? So when we're talking about this charge, right? This charge is directly proportional to the number of electrons, isn't it? Okay. So how much electrons has to come into this solution to convert that SN4+ to SN2+? Okay. Give it some thought. Try some stuff out. Think about it. And I'll give you a minute, and then we'll start. Okay. So we want this, and right now we have millimoles per hour right here, right? And this number is actually directly related to the number of electrons, isn't it? So what all do we have to do? Well, 1 SN4+ is going to require 2 electrons to convert to an SN2+, right? And so that's going to be a 2 electron for every 1 SN4+, right? This right here is our number that we were just given. So we're going to convert this to moles of electrons that pass through per hour. Okay. Now, we have millimoles of electrons per hour now, but that's not a current, is it? It's really close to a current. Really close to a current, in fact. It's called an amp hour, actually. Okay. But normally current is done in seconds, isn't it? Not in hours. Okay. By the way, if you're wondering about the devices all around you all the time, and you've heard numbers like kilowatt hour and amp hour, AMPH, or A lowercase h, those are the amps per hour, or the kilowatts per hour. Okay. Okay, so this is our number we just got. This is the millimoles of electrons per hour. We need to convert that to seconds by dividing it by 3,600 seconds, which is how many seconds are an hour. Anybody have any questions there? Okay. Once you have that, you can convert the millimoles back into moles, which means adding -3 on the top there. So 10 to the negative 6 instead, because milli is a 1 in 1,000. 1,000 millimoles per mole. All right. Now, if we want the actual current here, notice that we now have to use coulombs, right? We have to actually take a Faraday and solve this. So we have our moles per second of electrons. We need to take the coulombs per moles for electrons. Multiply that Faraday's constant by our number we got, and that's going to give us a coulomb per second, which is an amp. Notice if you want milliamps, you can just take that, multiply it by 1,000. You could have actually also just kept it as milli before, if you had wanted milliamps at the end. But just in case you need to do that. Milliamps is very, very commonly used in these situations. So you can get whole numbers. Okay, let's talk about electric potentials. So any electric charge is going to create what's called an electric potential. This is going to attract or repel charged particles. The electric potential difference is E. So this is going to be the potential difference when applied to electric systems. Okay? And it has to do with the charge imbalance. Okay? The easiest way to think about these are probably going to be like water systems in your head. It does introduce a few errors and a few problems, okay? So if you end up going much, much more advanced into electrochemistry or really into electricity in general, you're going to start using other models, or you're going to start grasping it without having to use models, okay? But the easiest model to work with, and it works 90-something% of the time, it works really great, is actually thinking of it like water pipes or like waterfalls, okay? So an electric potential difference is going to be the sort of difference you would see from like a waterfall height, okay? So it's how much energy is released when the thing lands on the bottom, right? That's how much it drives that energy forward, right? It's the potential energy difference, okay? Kind of like the height we're at right now is the potential energy difference due to gravity. So, between 2 points, this is going to be the work required, or which can be done with a unit charge moves from one point to the other. These potential energy differences are going to be measured in volts. That's actually the numbers I was using up there when I was talking about that. That was V for volts. And that's actually what you've seen a lot of in your life if you're like looking at, you guys know on like your power bricks, right? It has the number of volts that you need. You are aware of this? Or like batteries are for different volts? Mm-hmm.
So the electrical output, like out of your house and things like that,
Mm-hmm.
whenever you plug up an extension cord,
Yes.
do those extension cords limit the amount?
Okay, so yes, it reduces the volts that can come out. And in fact, the length of your wire always reduces the volts that can come out because your potential drops along the wire. But having said that, it does it fairly little as long as it's a reasonable quality wire. And in reality, your volts, the wire that most wires could handle a higher volt than what they're done. They're limited to a voltage based on the size of the wiring. Because if you get too thin of a wire, what ends up happening is, think about like hooking a hose to a little tiny hose, like one of the lab hoses, to like your water hose at your house. It would blow it up, right? That's what happens to most extension cords. So if you hook a undervolted or under amperage extension cord, you will actually cause it to heat up. It will then fuse and it will short. If you're lucky. If you're not lucky, it might electrocute you a little bit. But yeah. And so you see this fairly often actually at like work sites. They'll use like residential ones, and then they'll try to pass over way too many amps and way too many volts, like 5 times what they should be doing. Yeah. And it'll work for a while, but eventually it'll heat up. And if you ever feel one of your cords get really hot and you're not out in the sun, then that's what's happening. Residential, it's a disaster because it can heat up in the wall and then it lights the wall on fire. Yeah. And you see this a lot with like people doing this with like plugs, those extension cord plugs where it has a bunch of plugs on them. And they like chain them off their wall outlet. I know, you probably do.
There's like 3 outlets.
Mm-hmm. So that's the danger, actually. Every additional leg increases the resistance, is what it's called, and is causing the voltage to have to go through that resistance. Now, if you put an object in the flow of water, right, what happens? Well, it pushes against it, doesn't it? And it starts dispersing energy all around. That's called heat in this case, right? And so those resistances are all going to radiate heat. If your heat gets large enough, you can cause it to start like fusing. And when that happens, the resistance goes up really fast and the heat goes up really fast, and you can actually light it on fire. Okay. So if you're going to use one outlet that goes into a bunch of outlets, use one that's actually designed like that. Because what they'll have is they'll actually have quick shutoffs. Okay.
Like a surge protector.
Exactly. Yeah. There's other things in them than just surge protectors. But yes. Yes. It'll keep you from at least lighting on fire. It'll have its own breaker that will flip off. Yeah. And it'll actually show you if it's struggling or there's anything wrong. It'll change the light color. Yeah, I've actually seen one do that before. Yeah, which is nice. Get one that has an insurance policy, by the way, if you have anything really important. Mm-hmm. Yeah, they make them that they'll actually, within 10 years, pay for anything that's electrocuted on it. Yeah. So if you get one of those on your like super expensive computer or, EV or whatever you have plugged into it, probably not an EV, hopefully, but whatever you have that you want to protect. Yeah. I actually had a surge take out the infrared spectrometer at Bethel University. Yeah, and they did not have it on a surge protector. Very common, especially the electrical grids have been getting worse and worse lately as they introduce more alternative power sources because they can't control them as easily. But, like, honestly, it'll fix itself. It's just, they're currently in a sort of experimental phase. So, very worth doing. So this is a really good analogy for, like, voltage, right? So if you lift to a higher voltage, what's going to happen to the water? It's going to come out with more force, right? And it's going to come out with a faster flow, okay? Which means it can come out with more amperage. Right? Now, does the size of a waterfall do anything about how hard the water comes down at the bottom? So if we look at a little tiny waterfall that's like this wide, okay? And it's the same height, okay? Versus a huge waterfall like Niagara, right? Very, very wide, right? Doesn't have anything to do with how hard the water comes off, right? Or how fast the water flows through that specific area, right? Okay. So keep in mind that voltage has nothing to do with how much you flow through it, okay? It's the potential energy difference, right? And it's more analogous to height than it is the potential energy difference like a delta G or a delta H. So the number of moles for a voltage, an electric potential difference, or electromotive force, also EMF, does not affect the voltage. Okay? Okay. So again, here's how these relate to each other. You may recognize this from like Physics 2 if you've taken it. Also from a variety of different chemistry courses. It comes up fairly often. So when you charge, Q moves through the potential difference, E. Work required to move charge to a higher energy or work done by a charge moving to a lower energy is going to equal. So work is measured in energy, which is joules in this case, volts, which is E, times Q, which is coulombs. Okay. So what you'll notice is that work again is going to be in dimension of energy, joules. 1 volt actually equals 1 joule per coulomb. That's actually how those are related to each other. Okay. So how much work can be done by a 2.4 millimole electrons moving from a region with a potential of 0 volts to a region with a potential of 0.27 volts, or between any 2 points that differ by a potential of positive 0.27 volts, right? It doesn't actually matter where it is. If you were 0.27 volts difference, you're going to be the same problem anyways, right? Like if you were jumping down from the 3rd floor to the 2nd floor, is it any worse on your knees than jumping from the 2nd to the 1st? No. No, not really, right? Okay. Let's start that calculation. So I basically just added another equation on top of the calculation we did before, right? So we just do the same sort of calculation as we did in the previous problem, but now we've added to the work. Okay. All right. So if we take that previous calculation, it was charge equals N times the moles times Faraday's constant. So we have a 1 times 2.4 times 10 to the negative 3 moles, and then Faraday's constant there. That gives us our coulombs. Once we have our coulombs, well, we can use that in the work equation we just discovered, that we just talked about. And so we take our volts, 0.27 volts, times our coulombs here, and that's going to give us joules. And that gives us the answer of our problem. Now, if we were to instead move 2.4 millimoles of sodium cations with a potential of 0 to 0.27 volts, that would still be 62 joules of work, right? And again, it's because they're going to be repelled by the more positive potential, right? It doesn't matter if we're moving from moving positive things, if we're moving negative things, if we're still building up that same level of potential, it's the same answer, right? It doesn't actually matter what the mass is in terms of the electric potential here, as long as it can move. Okay, so let's talk about heat and work. So heat, Q, flows from the surroundings to the system, is positive. Heat Q flow from the system to the surroundings, that is negative. Work done in a system is going to be positive. Work done on the surroundings is going to be negative because your energy is flowing out of your system. Hopefully you guys all have explored that in physical chemistry and other courses a little bit. Okay. So this is actually our combination of all the previous calculations that we've talked about. And so the maximum work per mole of a specified product equals your delta G. You can obtain this between the free energy difference for an electrochemical reaction and the electrical potential difference, E, by an electrochemical cell. And so if we go ahead and work this out, we get delta G equals negative NFE. N right here is going to be unit charges per molecule. F right here is going to be the Faraday constant. And then E right here is potential difference in volts. And that will give us our delta G, which is joules per mole. Notice again, we don't get rid of the moles here. We don't want to get rid of moles because we're going to end up in moles. Okay? So if you ever try to derive this yourself, that's the difference. Again, though, note that negative delta G, right, is spontaneous. And so a high E value is going to be correlated directly with a negative delta G value. Okay? So if you go up to a positive change in E, that's going to be a what sort of process? you have a positive E. That's going to be a spontaneous process, right? If you have a negative E, what is that going to be? Non-spontaneous, or it's spontaneous in the opposite direction oftentimes, because electricity moves really well. Okay. So this right here shows the amount of energy produced by a size AA alkaline battery. And so you can see here, regardless of the rate at which it's discharged, you get the same sort of energy that's produced. The more negative means the energy, either heat or work. So now this green line right here shows the discharge rate strongly affects the AA battery efficiency. So when a AA battery is slowly discharged, the greater portion of its energy can be used for work. The faster the AA is discharged, the more that energy is going to be used for things that are other than work. And so that would be what we consider less efficient. And specifically, this is going to be things like the heat that's discharged. So, anybody have any questions there? You ready for resistance and power? All right. So power, this is P, is going to be the work done per unit time. And so the SI unit of power is the watt. The watt is going to be a joule per second. Notice that you also see power sometimes done. It's not actually power. It's called volt amps, which is labeled VA. Okay? So be aware that sometimes you will see VA. There is a small difference. Now, this again is going to be the work over time. So if we go ahead and put our equation terms in here, we would get EQ over T. We can rearrange this to Q over T right here. And E, what you'll notice is that Q over T is actually the same thing as current. And so you can do power equals the E right here, which is typically volts, right? This right here, which is amps typically. And so power equals the volts times the amps in theory. Okay? But overall, for your calculations, this is always going to work that way because we won't do the more advanced stuff when it comes down to electricity. If you're interested in that, there are courses on that. Okay. Ohm's law, this is going to state that the current is directly proportional to the potential difference across a circuit and inversely proportional to the resistance. The resistance is going to be R of the circuit. And so the resistance is going to be how well does this substance conduct that electricity. Okay? What is blocking the flow of that current? And so you get current equals E over R. The units of resistance is ohms, and that's the resistance units. By the way, you'll also see ohms show up in things like how pure is water, or like how much does a bass sound. And again, those are actually related terms. The purity of water, or the purer the water is, the more resistance it exhibits. And so that actually is a direct measurement to purity of water. Pretty easy measurement to make. The greater the voltage, the more current that will flow. The greater the resistance, the less current that will flow. And so, for example, you have your electric devices right there. You spill water on it. Why does it electrocute you? Okay, so your potential is not changed, is it? Until the breaker flips. Because you're being electrocuted. Okay? So that's the one thing not changing here, right? Typically, the electricity would have to pass through the air to electrocute you right now, right? Or the plastic body of your computer, one of the two. And so those have very high resistances, right? What happens if you bridge that gap with something that has a lower resistance? You get electrocuted, don't you? Because all of a sudden, that current that can flow, if this term goes down, increases tremendously, doesn't it? Okay. Right now, this term is really, really high. You splash water all over yourself in the computer, this term becomes very, very low. Well, much lower. Water's not a super great conductor. What if you put a copper wire in there into the power outlet? Is that a good idea? No, because you're reducing this resistance right here tremendously, aren't you? Okay. What if the electric difference, the energy difference is huge? The EMF is just massive, like in the case of a lightning. What happens? It can overcome the resistance, can't it? Okay. And so it still has enough amperage after that resistance to electrocute you, to harm you. Okay. Okay, so let's talk about using Ohm's law. And the battery generates a potential difference of 3 volts, and the resistor has a resistance of 100 ohms. The wire connecting the battery and the resistor is going to have a negligible resistance. This is the sort of games that are played oftentimes in these entry-level problems for electricity. Real wire has resistance, but we reduce that resistance to 0 because it makes the calculation easier. Okay? And honestly, in most cases, it's relatively negligible in comparison to an actual resistor. Let's find the current and power delivered by that battery. So we're just going to use the the equation we just talked about, right? And so E over R gives you I, the current. So we take the number of volts, we divide it by ohms. That's going to give us amps. If we want it in nice round whole numbers, we typically would work in milliamps. Okay. Now, what is the power that's produced by this battery? Well, again, now we have that current, right? And we have the E, and so we can multiply those two values. This is going to give us milliwatts because we don't have any other terms that we have to consider here. Okay. In a real, actual electrical system like your house, okay, or a power plant, this is going to be called VA voltamps. In a theoretical system like this, where you can limit all the options and you don't have any resistance for wires and blah, 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 this can be watts. Okay. If you do this for your house, though, know that these numbers will not perfectly be the same. Okay. So if you were to calculate this for your house or something that's a real system, this could be like 91 watts instead. It could be 89 watts. It could be a bit different. And if there's a lot more differences than the ideal system, it could be considerably different, which is fairly unusual actually, but usually they're pretty close, within like a 10%. Okay. Now, the relationship between charge and moles is this one right here. Work and voltage is that one. That right there is your free energy difference. That right there is your Ohm's law, and this is your electrical power here. Let's talk about cells now. So galvanic cells or voltaic cells, I typically call them voltaic cells, and most people I've talked to call them voltaic cells, but both will work. This uses a spontaneous chemical reaction to generate electricity. Does this sound like something that you know? Yeah, it sounds like a battery, right? In a galvanic cell, oxidizing and reducing agents are actually going to be physically separated in some way. This can be phase separations. This can be spatial separations. The electrons are then forced to flow through a wire to go from one reactant to the other. If you put both of these things together and they are no longer separated in any way whatsoever, will a galvanic cell actually do anything? So can you run a water wheel off of a typical lake? No, because it just goes back and forth, right? So you have a lot of difficulty running the water wheel. So you need a separation between the water being at high potential and low potential, right? So it can power things. Okay, this is why they do a separation of some sort, where the wire is the only option for the electricity to pass through. Okay, otherwise it won't do anything across the wire. It's more likely to just do it in the solution. So the battery, this was shown, was actually invented by Alessandro Volta. You can probably imagine where volt came from. In 1799. It actually consists of layers of zinc and silver separated by cardboard right here, soaked in brine. This was actually the first saltwater bridges, were these cardboard soaked in saltwater brine. This is a more typical sort of battery that you would see now. And so this is going to have 2 electrodes suspended in a solution of cadmium chloride. And so what you'd see here is your electrodes. Anode, by the way, means way up in Greek. Cathode means way down in Greek. And so literally an anode is where the electrons come from, way up. Electrons are coming up. Cathode is where the electrons go down into. And so cathode, electrons go down into. Okay. All the other language was actually derived from this. In case you're ever like, that doesn't really make sense to me. It's all from this. Okay. By the way, if you were to put electrons down here, what is being done at this point right here? The one where the electrons is coming onto things. Electrons going onto something is a reduction, right? Reductions produce things that are more negatively charged, don't they? Which is a cation, isn't it? Okay. Anode, on the other hand, is pulling electrons away from things, right? Pulling electrons away from things is a oxidation, isn't it? Okay. If you pull electrons away from something, it tends to produce what? Okay. Electrons away from things can produce the positive cations. Electrons onto things produce the negative anions, right? Okay. Or another way of thinking of this is the anode here has the anions coming towards it, right? And getting electrons pulled away. Okay. So again, reduction at the cathode, oxidation at the anode. That's the important part that you very, very much need to remember and understand. Okay, what happens at the cathode? Very good. What happens at the anode? Oxidation. Very good. Okay, so this where we've taken these 2 parts of this reaction and split it apart. This is called a half reaction on each side. So we've taken the reduction, we have it physically separated in some way from the oxidation, and the electrons are moving through this wire. These electrons moving through this wire is doing the work that we think of as electricity. Is electricity the electrons? No, the power in the electricity is the moving of the electrons, right? Not the electrons themselves. Okay. There's some interesting side effects to this. The power and work that's done by electricity actually moves in the electromagnetic waves, and so can theoretically move the speed of light. Yeah. Okay. So these are the 2 half reactions being written out right here. We have our reduction and our oxidation. Note that the number of electrons have to be changed to match here. And we can get then our net reaction right down here. Okay. What always has to be true about the electrons for a reduction versus an oxidation? The electrons are always a reactant in the reduction, right? They always have to be a product in the oxidation. Oxidation loses the electrons, reduction gains the electrons. So a voltmeter in the circuit, this can measure your difference in electrical potential, the voltage difference. That's why it's called a voltmeter, right? Volt, meter meaning measure. So this is going to happen between the 2 metal electrodes. What's actually being measured is going to be the difference between the voltage on your positive side and your voltage on your negative side. So E plus is going to be the potential of your electrode attached to your positive terminal. E minus is going to be the potential of the electrode attached to the negative terminal. Okay. So if we go ahead and calculate the voltage that would be measured by a voltmeter figure right here, the delta G is negative 150 kilojoules per mole of CD. What we'd have to do is we'd have to work back from that energy in joules per mole, right? And so that right there is a delta G. You may remember delta G equals negative NFE, right? So we go ahead and solve for that. Get E on by itself on one side. Now, 5 right here is going to be the number of N, because that's the number of electrons per atom transferred for our net reaction when we write that. I'm sorry, not 5. 2. 2, excuse me. I was looking. I was thinking of figure 14.5. It's 2 electrons transferred every time that reaction goes one step, right? Everybody good with that? Right there. All right. So we put our number negative 150. This is kilojoules, so it has to be times 10 to the third. We can cancel the negatives out right here, so that's going into giving us positive. We divide it by 2, and then we divide it by Faraday's constant. And so that gives us a 0.777 voltage. That is a spontaneous chemical reaction. It's a negative delta G. It'll produce a positive voltage. And so this spontaneous chemical reaction could be put with something that needs 7.777 volts or less to power it. Okay. All right, so again, negative charge. Electrons are going to move towards the positive electrical potential. In this case right here, the silver electrode is going to be positive with respect to the CD electrode. So the electrons will move from the CD to the AG right here. This is positive again because you're going to have these electrons moving off into the solution, forming this reaction right here, where we'll have the silver releasing our chloride into the solution. That's actually where those electrons go. So this is actually the intended reaction for this cell. Again, that is that net reaction right here. Note that this cell right here that we were looking at, this would do this reaction for only a temporary amount of time. As you do this reaction, what would happen is your charge would build up over time. And finally, you would come to equilibrium, right? What's true at equilibrium? Well, delta G is 0, isn't it? Okay. And so then you would have no overall voltage, no electricity is passing, and congratulations, you've killed yourself. Okay. And this would happen pretty quick. Like, this would not take very long to do. Very likely this cell would die within minutes, if not seconds. And so there's a added piece here that we have not talked about yet, which is called a salt bridge, and we've already kind of mentioned it. But again, that net reaction is going to be spontaneous. Very little current would flow from the circuit right here because the Ag plus is not forced to be reduced at the Ag electrode. It can just as well be reduced right over here at the other electrode. It has free reign, free flow, right? So this would actually short itself out very quickly. Okay, and then you'd have no flow of electrons through the wire at all. And so what we can do to prevent this is we split this up into what are called half cells. So each cell would have one of the oxidation or reduction reactions. Each cell would have its own. It would have the anode or the cathode. This would be the anode side right here. This is the cathode side. And we separate these through what's called a salt bridge. And we have to separate them through a salt bridge because if you build up positive charge on one side or negative charge on the other, you're going to end up, again, forming equilibrium, aren't you? Okay. Or another way of thinking about this is, what was causing this EMF right here? Well, we have an imbalance, right? And so if we allow it to balance, it will, again, reach equilibrium eventually. Okay, this will take a little bit longer than the other one would have, but it will still eventually reach equilibrium fairly quickly. So what we have to do is we have to have a way for the charges to rebalance themselves. And what we do is we put a third salt in here that doesn't actually take place in this reaction. That's actually going to allow us to rebalance the charges as you would build up negative charge over here and positive charge over here. Okay. Okay, so this is going to be a variety of things. These salt bridges can be all sorts of stuff, but the most common is things like a porous glass fritter containing a high concentration of potassium and nitrate, or any other electrolyte that does not affect the cell reaction, doesn't react individually. It just needs to be highly soluble and needs to be able to balance the charges. That's it. And relatively inert. So that porous glass frit right here actually allows ions to diffuse. It'll minimize the mixing of your solutions inside and outside the cell. This would not work if you just put salt in here, by the way, and nothing else, because then your fluids right here would mix eventually, right? And you'd be back to square one. Okay. So it needs something. You can do this with cardboard, like we mentioned, by the way. Remember, he used salt water on cardboard. That also would work. To prevent charge buildup in each half cell, we have the potassiums that can balance out the negative charges over here. We have the nitrates that can go on the other side and balance out the positive charges. And so it helps us buy time as we balance out these charges. Now, reactions that do not involve silver or other species that react with chloride, your salt bridge usually contains chloride, and so KCl is the more common. You might actually recognize that as being what you've been using the pH meter. Remember the pH meter you've been using all this time? It's actually what that's stored in, isn't it? Okay. And so, yes, that is an example of something that's very analogous to a salt bridge. Okay, the little glass ball at the end. Okay. Okay, and so this is some of the notations right here and how to read them. So the design of a galvanic cell is summarized using what's called line notation. The single line here represents a phase boundary. So this would be between like a solid electrode and a liquid solution, but this can be any phase boundary. If you have any way of separating these at all, it's a phase boundary. You're fine. Okay. They can be liquids, they could be solids, they could be aqueous, whatever, as long as it's in different phases. You put a line right here. If it was not in different phases, you wouldn't put a line here. Okay. Now, a double line right here is going to represent the salt bridge. And so this right here is the salt bridge right there. That's the double line. The electrodes are going to be shown at the extreme left and right-hand sides. The electrodes typically are going to be solids. They don't have to be, though, but more often than not, they are the solids. And so, for example, right here, you're going to show your anode, which is that one right there. You have a phase boundary separation, and this is going to be the salt that's surrounding it, the CdNO3 That is going to be your electrolyte right there. This right here is going to be the electrolyte right there, and then it's going to be the silver, which is the solid, which is your cathode. Everybody okay with that so far? Okay. The formatting of this is actually incredibly important. Notice that on this side, you're going from a solid to a salt, which means you have lost electrons, haven't you? So do you see that that's actually the half reaction, isn't it? Okay. On this side over here, you have gained electrons and went to the solid, right? Which is this half reaction over here that happens on the cathode. Okay. Can everybody see it all right? Okay. Practice reading those because it's actually quite important for this chapter. Okay. All right. So this is actually Apollo fuel right here, in case you're wondering. This is a fuel cell in this case. It actually used 3 of these units on the Apollo, and it's going to have liquid oxygen, for the spacecraft's fuel cell. It actually exploded. These fuel cells were developed in the 1960s. They were one of the most efficient methods to provide electricity in space. They're still heavily being used. There's actually fuel cells that are currently in use in production. They are a thing that is slowly working its way into the private market, but they are much more complex, but much more efficient. than a traditional like engine or and it's because they actually do they actually do these redox reactions in a very modulated manner. Okay. Everybody remembers the difference between reversible and irreversible? Yeah. Okay. So if you do a reaction reversibly, you can waste a lot less energy because you do it step by step, very small steps. If you do a reaction irreversibly, you tend to waste a lot of energy as things like heat. Okay. Which when you're like driving a car or you're trying to produce electricity, heat is not necessarily a great thing to be producing. In fact, most of that's waste. Okay. By the way, does anybody know how efficient a space heater is? Well, waste energy is heat, right? So a space heater is always 100% efficiency because its job is to produce waste heat. Now, it may not get you heated 100% efficiently, but it certainly converts electricity to heat 100% efficiency. Or at least very, very close to. Unless it's electrocuting, I guess. Now, this right here is a hydrogen-oxygen fuel cell. You may have heard of these before. They are currently on the market, though I have not seen them in widespread use yet. There's some problems, especially on like the production chain. There's some huge problems. So this is a modern hydrogen-oxygen fuel cell, and it's going to derive energy from a net combination of H2 and O2 to form water. This is why they're really popular. The H2 is actually going to be converted to H plus and electrons at the anode. And so you have electricity being produced right here, the electrons separating, and you have H plus being produced. The electrons are going to pass through a circuit. They'll do some sort of useful work, power something, etc. Again, these are currently being done, being used. The H plus will then pass through a membrane of some sort. There's actually a whole variety of membranes that you can use here. Teflon chains with sulfonic acid is one of the newer, more interesting ones that seems to be working really well. Again, the H plus passes through the membrane here. H plus will then combine with oxygen at your cathode. This will form H2O, which is water. Note that, again, your air just gets pulled in the same as you would like breathing right now. And so this is then going to release the water, and water is one of the most benign substances that you can release as a waste product, right? Now, anybody know what actually causes the majority of global warming right now? Yeah, water. So, but again, we don't have any choice on that. It's not going to do it either way. Okay. These are some different batteries. I think I have all of these in the PowerPoint. My previous semester's lecture. You all have a great day. I won't see you Wednesday.